Thank you. I will start.
Now we can see.
Hello, I'm Sho Kajihara from the University of Electrocommunications, Japan. First of all, I'd like to appreciate the organizers who gave me the opportunity of presenting my research and rescheduled my presentation time. Today, I'd like to talk about generating duplex routes for robust bus transport network by improved multi-objective evolutionary algorithm based on decomposition. The outline of my talk is summarized as follows. Firstly, I explain background, followed by the previous works, approach, the route network design problem. Then I introduce the proposed method, which integrates the new cost of operation with a new solution update mechanism, while maintaining the diversity of solutions. Afterward, I explain the experiments, show results, and discuss the results. When disaster occurs, the train will be dysfunctional because rail lines are destroyed, as shown on the left side of the figure. For such a situation, the bus, as shown on the right side of the figure, can. The outline of my talk is summarized as follows. Firstly, I explain the background, followed by the previous works, our approach, the route network design problem. Then I introduce the proposed method, which integrates a new cost of operation with a new solution update mechanism, while maintaining the diversity of solutions. Afterward, I explain the experiments, show results, and discuss the results. When disaster occurs, the train will be dysfunctional because rail lines are destroyed, as shown on the left side of the figure. For such a situation, the bus, as shown on the right side of the figure, can take detours even when roads are destroyed. From this advantage, in the Great East Japan earthquake in 2011, many people took buses at that time. However, what should be noted here is that we cannot predict when the environmental changes, such as the road destruction and collapse of the bus stop occur. To cope with such change, the transport network should be modified. However, it goes without saying that the modification of the transport network confuses passengers. This suggests that it is important to build a robust bus transport network that does not need the modification of its network. To tackle this problem, the following approaches have been proposed. First, Kitagawa's method divides an infrastructure network to make the route and connect them in order to minimize to suffer from a change of road condition, as shown on the left side of the figure. In this figure, the infrastructure network is divided into three areas. The routes are generated within each area, and they are connected to generate the whole route network. As a feature of this approach, the short routes are not damaged in high possibility in comparison with the long routes. However, this approach still needs a modification of the transport network in the case of the road destruction. Second, Morimoto's method redistributes the buses among the routes to suppose the routes that the number of passengers increases as shown on the right side of the figure. In this figure, the appropriate number of buses are redistributed. In this example, the two green buses are assigned to the red route, and the one yellow buses are assigned to the blue route. This approach can cope with the demand change, but it is hard to cope with the road destruction. To adapt to environmental change without the modification of the transport network, I propose the concept of the duplex route network. The duplex routes do not simply mean the duplicate routes, but mean the routes where the bus stops belong to more than two routes. Such stops can serve the transfer points and provide alternative routes. Thanks to this feature, the passenger can take the green route as a detour when the section between 2 and 5 is destroyed. As the other example, the green route can be removed when the bus stop 9 is destroyed because other route covers the bus stop of the green route. In this example, the bus stops 5, 4, 2, 3, 6, 8, and 50 are covered by the red and blue routes. Before explaining the proposed method, let me introduce the route network design problem in the next slide. In root network design problem, the infrastructure network and the origin destination table are given as input, and the optimized root network and the appropriate number of buses are calculated as output. Here, the origin destination table shows the passenger demand. For example, the demand from bus stop 1 to bus stop 2 is 400 passengers. As evaluation criteria, root network design problem as a minimization problem employs the following two criteria, F1 and F2. F1 indicates the passenger travel time, which includes the travel time, waiting time, and transfer time, while F2 indicates the total number of buses. As a characteristic of this problem, it is an NP-hard combinatory optimization problem. For such a problem, evolutionary computation is one of the potential approaches to tackle it. To optimize a root network with a duplex root, the MOEA algorithm is employed as a baseline method and is improved to evolve the duplex root network. As most of you know, MOEA distributes the weight vectors, which are represented by the gray arrows, and determine the search direction of the solution. The brief algorithm is summarized as follows. In the initialization phase, the population is generated. Here, one solution corresponds to one root network. In the parent selection, when focusing on the red weight vectors, two individuals as a solution are selected from neighbors colored by the red circle. In this phase, the crossover between neighbor solution is very important to generate the duplex root because the neighbors have a similar topology so that the new solution can inherit the parent's characteristics, including the duplex roots. This is a reason why MOED is employed in this research. After a new solution is generated, it is compared with the neighbor solution in the scalar fitness value, and the neighbor solutions are replaced by the new solution when the new solution outperforms the neighbor ones. Since MOED is not designed to generate the duplex root, the two mechanisms for duplex roots and maintaining diversity are proposed to integrate them into MOED. First, the crossover operations is improved to generate the duplex root. The center figure shows the image of before and after generating duplex roots, where the duplex bus stops are indicated by the orange circle. By the proposed crossover operation, the duplex root, which have the duplex bus stops, are generated, which contributes to increase the number of the duplex routes. Second, the priority update mechanism is improved to select the duplex root network that updates the parent's root network. This mechanism contributes to keep or increase the number of the duplex routes. As the other feature of the priority update mechanism, it can maintain the diversity of the root network by changing the number of the solution updates. Such a diversity is indispensable to explore the good root networks, especially in the case of generating the similar root networks through the crossover operation. The right side of the figure shows the image of decreasing the diversity of solutions and maintaining the diversity of the solutions. Since the multiple solutions in MOED tend to be replaced by the one good solutions, which decrease the diversity of the solution, as shown in this figure. The only one solution is replaced by the one good solution in this research to maintain the diversity of the solution, as shown in this figure. To understand the details of the proposed course of operation, let me explain it. In this figure, the solid line indicates the existing routes, and the dotted line indicates the new routes. Here, these bus stops are called duplex bus stops because they are shared with some routes. Among these duplex bus stops, this bus stop is also called the new duplex bus stops because this bus stop is newly duplexed by adding the red route. Since we want to generate a network that has a duplex route, the proposed method aims to increase the number of new duplex bus stops. For this purpose, the crossover in SEM2 employed in this research is improved for duplex routes. Since MOED itself cannot evolve the feasible solutions, the crossover in SEM2 is required to evolve them. In the concrete operation, one root is selected randomly from parent 1 and added to the offspring. In this figure, root 3 is selected and becomes existing root. After that, the crossover in SEM2 calculates the duplex bus stop rate with the existing root. In other words, the percentage of the bus stops that are shared with the root 3 is calculated. And the root with the lowest duplex bus stop rate, the root D in this case, is added to the offspring. Since the duplex bus stop rate will be the same because most bus stops are included in the existing root, the proposed crossover operation improved from the crossover in SEM2 calculates the number of the new duplex bus stops and select the root with highest new duplex bus stops, the root C in this case. Such a root addition continues until the size of the offspring is the same as that of the parent one. After generating the offspring, MOEA determines whether the solution should be updated or not, according to the scalar fitness. Since MOEA does not have the mechanism of increasing the number of the duplex root, as mentioned before, the proposed mechanism replaces the neighbor solution with the offspring, not only when the scalar fitness is improved, but also when the number of the new duplex bus stops increases. In this figure, the blue circle indicates the offspring, and the red circle indicates the parent solution. From the viewpoint of the scalar fitness, the blue offspring outperforms the red parent solution, which satisfies condition 1. From the viewpoint of the number of duplex bus stops, represented by the orange circle, on the other hand, the number of the duplex bus stops of the blue offspring 4T is larger than that of the red parent 30, which satisfies condition 2. Since two conditions are satisfied, the blue offspring updates the red parent solution. In addition to the solution update, it is very important to maintain the diversity of solutions for exploring the good root network that has a larger number of the new duplex bus stops. To address this issue, this research employs a priority update mechanism, which can change the number of solution updates. In MOED, the multiple neighbor solutions tend to be replaced with offspring if the offspring outperforms the neighbors. This decreases the diversity of solutions as shown on the left side of the figure. In MOED with priority update mechanism, on the other hand, the multiple neighbor solutions are compared with offspring in the order of the short distance from the weight vectors. And the NR number of neighbor solutions are updated if offspring outperform neighbors. In this figure, NR is 5. What should be noted here is that NR is set to 1 in this research, which means that only one neighbor solution is replaced with offspring if the offspring outperforms the neighbor solution. This contributes to maintaining the diversity of solutions. To investigate the effectiveness of the proposed mechanism integrated in MOED, this research conducted experiments on Mandl's benchmark problem, whose infrastructure network and demand table are shown on the right side of the figures, and the total demand is 50,570 persons. As a parameter setting, the population size is 70, the neighbor solution size is 5, the number of generations is 20, and the number of runs is 31. As evaluation criteria, the following criteria are employed. The first one is the percentage of the duplex bus stops, which measures how many number of the bus stops have been duplex among 50 bus stops. The second one is hypervolume, which evaluates the trade-off relationship between the total passenger travel time and the total number of buses. In the experiments, two cases are conducted. In case 1, the combination of the two proposed mechanisms are compared. Concretely, this research compares 1, 2, 1 plus 2, and none of 1, 2, which correspond to MOED with a crossover in SEM2. As mentioned before, MOED itself cannot evolve the feasible solutions, meaning that the crossover in SEM2 is required to evolve them. In case 2, the solution diversity mechanism is added in the combination of the two proposed mechanisms conducted in case 1. This is a result of the case 1. The upper right table represents the combination of the two proposed mechanisms. For example, the label D means the combination of the proposed crossover for duplex root and the proposed priority update for duplex root. The label A, in contrast, means none of the proposed mechanisms, which correspond to MOED with a crossover in CMO2. The upper left figure shows how the percentage of the duplex bus stops changes as the generation increases, while the lower right figure shows how hypervolume changes as the generation increases. In these figures, the vertical axis in the upper and lower figure respectively indicates the percentage of the duplex bus stops and hypervolume, while the horizontal axis in both figures indicates the generation. The yellow, green, blue, and red dotted lines indicate the result of the labels A, B, C, and D, respectively. These results show that the D is the best from the viewpoint of both the percentage of the duplex bus stops and hypervolume. The D is, of course, better than the MOED with a crossover in SEMO2. This suggests that the combination of the proposed crossover for duplex roots and the proposed priority update for duplex roots is important to improve both the percentage of the duplex bus stops and hypervolume. This is a result of the case 2. In detail, the result of case 2 are represented by the solid lines, and those of case 1 is represented by the dotted lines. The upper and lower figure show that all results are improved by adding the solution diversity mechanism. This suggests that the diversity of the solution contributes to improving both the percentage of the duplex bus stops and hypervolume. Since the effectiveness of the proposed mechanism has been verified through the numerical experiments, the next step is to investigate how the root networks generated by the combination C', B', and D' are different. This research analyzes it qualitatively by visualizing the generated root networks. This figure shows the root network of the combination C', where the left, center, and the right figures show the parent 1, parent 2, and offspring, respectively. The orange circle and the white rectangle indicate the duplex bus stops and not duplex bus stops, respectively. From the viewpoint of the duplex bus stops, the bus stops 9 and 40, marked with the green circles, are duplexed by the proposed crossover mechanism, even though the two parents are not duplexed. This contributes to generating the duplex root network. However, the sections between 6 and 8, 7 and 10, marked with the red circles, become more redundant than the parents. This is because the combination C' does not have the proposed priority update mechanism. That is, the similar root networks tend to be generated due to a lack of diversity of solutions. The crossover between such similar root networks easily generates redundant roots. Next, the root network of the combination B' is analyzed. Focusing on bus stop 5, 12, and 30, these bus stops are not duplexed, even though parent 1 or parent 2 is duplexed. This is because the combination B' does not have the proposed crossover mechanism. That is, the duplex bus stops are difficult to be generated because the offspring is generated without considering the duplex roots. From this fact, the offspring is hard to inherit the duplex bus stops from the parents. Finally, the root network of the combination D' is analyzed as the best root network. From the viewpoint of the duplex bus stops, all bus stops are duplexed by the proposed mechanism. This is because the duplex root network is generated by the proposed crossover, and such a good root network is selected to update the parent solutions. These results suggest that the combination D' contributes to increasing the number of duplex bus stops while increasing performance, that is, the total passenger travel time, the total number of buses. I would like to conclude my talk. Today, this research stresses the importance of the robust network generated by the duplex roots in order not to modify the root network in the case of environmental change. To tackle this issue, two proposed mechanisms are proposed to be integrated with MOED for the duplex roots. The first one is the crossover for duplex roots, and the second one is the priority update for duplex roots with the solution diversity mechanism. The results show the importance of the integration of two mechanisms to increase the number of duplex bus stops and the performance of the root network. As future work, the following research must be done in the near future. The first one is to verify the effectiveness of the proposed method with real-world data. The second one is to investigate in the dynamic environmental changes. Thank you for your kind attention.
Thank you, Sho. Very interesting work. Is there any question from the audience? No question. I have one question. It's more a suggestion than a question. Your work is very interesting. For sure, I will read the details into your paper. But I think that your implicit final goal is to improve the timings of the bus transportation. So the question is, do you think is it possible to integrate some objective like pollution minimization in your work?
In the real-world data?
Yes, I mean, you duplicate the roots of the buses, you have more buses, maybe these more buses make more pollution than before.
In my analysis, real-world bus network is not duplex. Almost 75% bus stops is duplex. So more duplex is needed, and we can more duplex by applying this method with real-world network, I think.
Okay, I'm co-author of the Sho Kajihara. I want to answer instead of him. Regarding to your the questions on the populations of the pollutions of the according to the bus, we can integrate such kinds of aspect to optimize for each buses. Currently, we assume that the size of the bus is the same, and but the other our colleagues change the type of the bus, and that can be integrated the amount of the pollutions for each buses. So right now we don't have such kind the result, but I hope that we can integrate it to consider the amount of the pollutions of the buses. So thank you very much for your kind suggestions.
Thank you for your answer.